Let's focus on step 6 of interpreting blood gases, assessing the p-AO2. To do this, we need to go through a few learning objectives. We're going to be able to write the alveolar gas equation and explain its use, define the respiratory quotient, define the normal AA gradient, and then, within a clinical scenario, calculate the p-AO2 and the AA gradient. Now let's refresh ourselves on a few things to remember about the p-AO2. It's only meaningful in arterial blood gases. It depends on the FiO2, or the fraction of inspired oxygen. It requires the AA gradient to fully interpret. That's the difference between the p-big-AO2, which is the alveolar oxygen pressure, and the p-AO2, which is the partial pressure of oxygen in the artery. And for healthy individuals breathing room air at sea level, the expected p-AO2 is somewhere between 80 and 100 millimeters of mercury. Now let's move on to the alveolar gas equation. The alveolar gas equation calculates the partial pressure of oxygen at the level of the alveolus, and it comes from Dalton's law. Now Dalton's law says that for the total pressure of any container, it's made up of the sub-pressures of all the components within the container. Assume the container is the alveolus. Well, the pressures within the alveolus are the pressure of oxygen, the pressure of water, the pressure of carbon dioxide, and the pressure of everything else, which is primarily nitrogen. So what is the total pressure? Well, the total pressure is the pressure of atmosphere. By convention, we usually think the pressure of atmosphere is the pressure of atmosphere at sea level, which is 760 millimeters of mercury. But as you know, since most of you live in Salt Lake City, the pressure can be something else. And in fact, in Salt Lake City in the mountains, the pressure is much smaller. Therefore, the container for which all the gases can combine is smaller. Or if you're in a hyperbaric oxygen chamber, that total container can be much, much larger. So let's again think about all the pressures that are contained within one alveolus. Here's the alveolus, and now let's focus on each of the partial pressures individually. First, let's focus on the pressure of water. By convention, the pressure of water is 47 millimeters of mercury. That comes from scientific studies, and it doesn't change whenever you're thinking about the alveolar gas equation. The other pressure we know of, generally, is the pressure of CO2. And the pressure of CO2 is, in normal individuals, 40 millimeters of mercury. So let's now think about the equation for what we have. We have the pressure of oxygen is equal to the pressure of atmosphere minus the pressure of water minus the pressure of CO2. Now, wait, there's this R factor here, and this often gets confusing. So let's pause and think about what R is. R is the respiratory quotient. And the respiratory quotient is a balance between CO2 production and oxygen consumption. This is driven by the proportions of fats, carbohydrates, and proteins, and it's traditionally calculated as 0.8 for a mixed human diet. This is more than most people need to know. What people need to know are the following. The alveolar gas equation represents a steady state of oxygen diffusion into the capillary and CO2 into the alveoli. And the respiratory quotient is literally the fudge factor that makes the alveolar gas equation work. Because when we go back to the Dalton's law, what we know is we know the partial pressure of CO2 in the artery. And we use that 0.8 to make it the partial pressure of oxygen in the alveoli. I'll say it again. That R factor allows us to take the partial pressure of CO2 in the artery and apply it to the alveolar gas equation using, again, the fudge factor. Now there's one last thing within Dalton's law that we haven't talked about, and that's the pressure of nitrogen, which is literally nitrogen and a few other things. This is where the fraction of inspired oxygen comes in. Within air, there is the fraction of oxygen, the fraction of nitrogen, and the fraction of all the other crap that we inhale. Again, room air is 0.21% oxygen. I think now that we've talked about Dalton's law and we've assessed that really the alveolar gas equation is just taking all of this partial pressures and combining them together to equal the total pressure within a compartment, we can then calculate the p-AO2, or the partial pressure of oxygen in the alveoli, using the alveolar gas equation. Let's start again with this figure. And for those teenage boys out here, let me clarify one more time. This is a picture of an alveolus. Now, let's think about the fraction of inspired oxygen again. Let's go through it one at a time. The fraction of inspired oxygen is 0.21. The total pressure of the compartment is the pressure of atmosphere, and by convention we say it's 760 millimeters. The pressure of water is 47 millimeters of mercury. And finally, the partial pressure of CO2 comes from the partial pressure of CO2 in the artery, which is traditionally 40. And then we have to use the respiratory quotient to convert that into the partial pressure of CO2 in the alveolus. And if we take all those numbers together, we get the partial pressure of oxygen in the alveolus at sea level, breathing room air, is equal to 100 millimeters of mercury. And thus there you get the normal partial pressure of oxygen in the blood is somewhere between 80 and 100 millimeters of mercury. Where does this come from? Well, let's review real quick. We've got the learning objectives, we've written the alveolar gas equation and explained its use, we've defined the respiratory quotient, and now we're going to talk about the AA gradient, the normal AA gradient. And then finally we're going to calculate the partial pressure of oxygen in the alveoli and the AA gradient within a clinical scenario. So, the alveolar arterial gradient. This is a diagram that shows the alveolus and the capillary. P big AO2 is in the alveolus, P little AO2 is in the capillary, at the end of the alveolar capillary unit. The normal difference between the P big AO2, the alveoli, and the capillary, or the artery, is 10 millimeters of mercury. It increases with the age and increases with FiO2. But this is how come the alveolar oxygen partial pressure is 100, but the arterial partial pressure of oxygen is somewhere between 80 and 100 in normal individuals. Finally, let's move on to a case. This is the case that you had in your workbook. A 26-year-old male with insulin-dependent diabetes and chronic kidney disease presents with pneumonia and glucose of 600. He's on 15 liters of oxygen via a non-rebreather mask. This is equal to 100% oxygen. That's an important key point. When you're on 15 liters of oxygen via a non-rebreather, you can assume the fraction of inspired oxygen is 1. So now let's calculate the P large AO2. We're going to use the alveolar gas equation, and let's go through it again one at a time. The fraction of inspired oxygen is 1. The total pressure of the compartment, or the pressure of atmosphere, is 760, minus the partial pressure of water, which is 47. And in this equation, we have the P little a CO2 of equal to 35. And then we have to divide it by 0.8, which is that respiratory quotient. So taking all these numbers together, we get the partial pressure of oxygen in the alveoli, or the P big AO2, is equal to 669 millimeters of mercury. This is the first step in defining the AA gradient. The next step is just to subtract P big A from P little a. So 669 millimeters of mercury minus 60 millimeters of mercury equals an AA gradient of 609 millimeters of mercury. This is huge and a sign that this patient has respiratory failure. Now, let's review the learning objectives one more time. We've written the alveolar gas equation and explained its use. We've defined the respiratory quotient. We've defined what the normal AA gradient is. And now you're able to calculate the partial pressure of oxygen in the alveoli and the AA gradient within a clinical scenario. I hope this gives you some background on understanding how to assess the P little AO2 in a blood gas, but clearly it takes lots of practice before you become experts at it. Thanks.